piezoelectric sensing elements, they are very, very common. The idea is that you use so-called crystals, and the difference between crystal and other materials is that the molecules are arranged in a grid, in a pattern. So you will have the molecules arranged in a given grid, like this, for example, here. I could go on drawing forever, but you see the molecules are arranged in some kind of a grid. Rutemønster på norsk. Okay, if you have the molecules arranged in a grid, this is illustrated here. It's because of the electrical charge of each and every molecule. They are balanced, so you have some that will be negatively charged and some will be positively charged, but they keep each other in place, and thus they will be arranged in a grid. So you will actually have this small little dot here is meant to illustrate the equilibrium of the charge. You see the minus molecules here, they will have their max charge point right in the middle here, while the blue ones will have the same, the max charge point right in the middle. So these two will balance each other, and therefore the net force, the net electrical field between them is zero. They balance out. So this system is at rest. What happens if I take such a crystal and squeeze it like this figure here shows? Well, what happens then is that you will find that the equilibrium or the charge center for the yellow dots is a bit above the charge center for the blue molecules, and therefore you will have a minus concentration up here, and you will have a plus concentration here. Since the blue dot is a bit below the yellow dot, you will have a minus on top and plus on bottom. So what you see if you squeeze this crystal is that you will be able actually to measure a voltage between the two. If you, on the other hand, stretch the same crystal, you will have the center point for the blue above and the center point for the yellow below. So a positive charge on above the negative charge, so you will have a net plus charge here and a net negative charge here, and you will be able to measure that as a voltage again, but with opposite polarity than compared to when you squeezed the crystal. Now, that was if I squeezed the crystal or I stretched the crystal, so we can actually use piezo crystals as a force sensor. If I apply a force here or I apply a negative force here, I can detect that. But they can also be used the other way around. What if I apply a voltage here from, for example, a battery? If I apply a voltage, well, that would change the shape of the piezo crystal. So it would actually make the crystal squeeze together or stretch apart. So how can that be used? Well, you all have them inside your cell phones, because many microphones and speakers are made from piezo crystals. What I have in a piezo microphone is that I apply air pressure waves from sound. Air pressure waves is change in pressure coming from the sound, And if I apply that to a piezo crystal, that crystal would vibrate, and the vibrations would be picked up as a change in voltage. On the other hand, if I applied a change in voltage to my piezo crystal, it would start to vibrate, and if I changed the frequency of those vibrations, this voltage, the frequency of the vibrations would change, and that would create a sound. So that would be a speaker. The properties of piezo crystal, this is an equivalent model. Of course, inside a piezo crystal you won't find capacitors and inductors, but you can model the internals of a piezo crystal as capacitors and inductors, and that actually makes a resonant response for a piezo crystal like this. So you have actually frequency dependent sensitivity. So in a region in the middle here you have a quite flat response, where you have a frequency band where the voltage force ratio is quite stable. Then you have a peak sensitivity right here, which will be corresponding to the resonant frequency of the device. It's very much like a church bell. Let's try to draw a church bell here. If I hit this church bell with a hammer, that would ring with a given frequency. That would be the resonant frequency of the church bell. Now, if I hit a piezo crystal with a short voltage, like this, a voltage pulse, a short voltage pulse like that, it will ring for a given time. And also, if I receive a ringing frequency, it will respond. It will be very responsive at that frequency. So, for some applications, you are very, very interested in this so-called usable region, where you have a flat response. Then you can use it as a force sensor, because the voltage force relation is in this region not very frequency dependent. But if I want to use it as in an ultrasonic device, which we will come back to, well, then we use it in this resonance part of the frequency response. We will come back to this region later when we talk about ultrasonic devices, but for now, as a force sensor, you must use it in this frequency region. What is this region? Which numbers do we have here? Well, that depends on what kind of piezo crystal you purchase. So there are many different versions out there, but be aware that they are frequency dependent. And also note that you can't use them without the frequency. So if I apply a force to a piezo crystal that is constant, well, then the signal would die out very, very soon. So you can use it, for example, as an accelerometer. Here you have a piezo crystal and you have a seismic mass. So when I try to accelerate this in this direction here, this part here is pushed upwards. This one would try to resist that change in velocity and therefore apply a force to the piezo crystal, which in turn produces a voltage. And then you have the ultrasonic transducer, which we will come back to when we talk about ultrasonics, but they are used in this region here. The accelerometer would be used in this region here. There is also something called piezo resistive sensing elements, and they actually have a changing resistance. So they are a bit different. They don't create their own voltage. They just have a resistance that is force dependent. And it's all down to the chain that you actually manipulate the band gap of the atomic structure. So it's not a part of the syllabus, it's for information purposes only, so you can read more about it on those two links there.